The history of Earth concerns the development of the planet Earth from its formation to the present day. Nearly all branches of natural science have contributed to the understanding of the main events of the Earth's past. The age of Earth is approximately one-third of the age of the universe. An immense amount of geological change has occurred in that time span, along then with biological change. Earth formed around 4.54 billion years ago by accretion from the solar nebula. Volcanic outgassing probably created the primordial atmosphere, then the ocean. But the atmosphere contained almost no oxygen, so would have been toxic to most modern life, including humans. Much of the Earth was molten because of frequent collisions with other bodies, which led to extreme volcanism. One very large collision is thought to have been responsible for forming the Moon. Over time, the Earth cooled, causing the formation of a solid crust, and allowing liquid water to exist on the surface. The first life forms appeared between 3.8 and 3.5 billion years ago. The earliest evidences for life on Earth are graphite, found to be biogenic in 3.7-billion-year-old metasedimentary rocks discovered in western Greenland, and microbial mat fossils found in 3.48 billion-year-old sandstone discovered in Western Australia. Photosynthetic life appeared around 2 billion years ago, enriching the atmosphere with oxygen. Life remained mostly small and microscopic until about 580 million years ago, when complex multicellular life arose. During the Cambrian period, it experienced a rapid diversification into most major phyla. More than 99% of all species, amounting to over 5 billion species, that ever lived on Earth are estimated to be extinct. Estimates on the number of Earth's current species range from 10 million to 14 million, of which about 1.2 million have been documented and over 86% have not yet been described. Geological change has been constantly occurring on Earth since the time of its formation, and biological change since the first appearance of life. Species continuously evolve, taking on new forms, splitting into daughter species, or going extinct in response to an ever-changing planet. The process of plate tectonics has played a major role in the shaping of Earth's oceans and continents, as well as the life they harbor. The biosphere, in turn, has had a significant effect on the atmosphere and other abiotic conditions on the Earth, such as the formation of the ozone layer, the proliferation of oxygen, and the creation of soil. Geologic timescale. The history of the Earth can be organized chronologically according to the geologic timescale, which is split into intervals based on stratigraphic analysis. The following four timelines show the geologic timescale. The first shows the entire time from the formation of the Earth to the present, but this compresses the most recent eon. Therefore, the second scale shows the most recent eon with an expanded scale. The second scale compresses the most recent era, so the most recent era is expanded in the third scale. Since the Quaternary is a very short period with short epochs, it is further expanded in the fourth scale. The second, third, and fourth timelines are therefore each subsections of their preceding timeline as indicated by asterisks. The Holocene is too small to be shown clearly on the third timeline on the right, another reason for expanding the fourth scale. The Pleistocene epoch. Q stands for the Quaternary period. Millions of years. Solar system formation. The standard model for the formation of the solar system is the solar nebula hypothesis. In this model, the solar system formed from a large, rotating cloud of interstellar dust and gas called the solar nebula. It was composed of hydrogen and helium created shortly after the Big Bang, 13.8 Ga, and heavier elements ejected by supernovae. About 4.5 Ga, the nebula began a contraction that may have been triggered by the shock wave of a nearby supernova. A shock wave would have also made the nebula rotate. As the cloud began to accelerate, its angular momentum, gravity and inertia flattened it into a protoplanetary disk perpendicular to its axis of rotation. Small perturbations due to collisions and the angular momentum of other large debris created the means by which kilometer-sized protoplanets began to form, orbiting the nebula center. The center of the nebula, not having much angular momentum, collapsed rapidly. The compression heating it until nuclear fusion of hydrogen into helium began. After more contraction, a T-Tauri star ignited and evolved into the Sun. Meanwhile, in the outer part of the nebula, gravity caused matter to condense around density perturbations and dust particles, and the rest of the protoplanetary disk began separating into rings. In a process known as runaway accretion, successively larger fragments of dust and debris clumped together to form planets. Earth formed in this manner about 4.54 billion years ago, and was largely completed within 10 to 20 million years. The solar wind of the newly formed T-Tauri star cleared out most of the material in the disk that had not already condensed into larger bodies. The same process is expected to produce accretion disks around virtually all newly forming stars in the universe, some of which yield planets. The Proto-Earth grew by accretion until its interior was hot enough to melt the heavy, siderophile metals, having higher densities than the silicates. These metals sank. This so-called iron catastrophe resulted in the separation of a primitive mantle and a core only 10 million years after the Earth began to form, producing the layered structure of Earth and setting up the formation of Earth's magnetic field. J.A. Jacobs was the first to suggest that the inner core, a solid center distinct from the liquid outer core, is freezing and growing out of the liquid outer core due to the gradual cooling of Earth's interior.